Hello all, welcome to the next module of Nyquist plot. I hope you all have revised the concepts that we have learned in the last two sections, that is critical point, zeros of 1 plus GSHs playing the part of closed loop poles, then contour mapping, and most importantly encirclements and the method to count the encirclements. Today we are going to study mapping theorem and then the Nyquist criteria, which is useful for commenting on the stability or analyzing the stability of a control system when the Nyquist plot is sketched. Let me share a screen with you now. Yeah, so let us start with the mapping theorem, which is also known as principle of argument. Now, as the first part, we will just see the theoretical representation or theoretical statement of mapping theorem, and then part by part we will try to understand it. Before going further, there are certain notations which we have discussed in last sessions also. F of s is analytic function and it is a single valued function. We do need to consider the contours except the singularities. That means at the points where the function becomes non-analytic, that means the value of the function becomes infinite. So we need to exclude those points when we are considering the contours. And f of s is analytic and single valued function. C is the contour in S plane and CF is the contour in F of S plane, which is obtained after the mapping method. We have seen mapping also, excuse me. Now, the mapping theorem states that if f of s is a single valued function that has finite number of poles and zeros in S plane, and C is a contour in S plane that does not pass through any of the poles or zeros of f of s, that means it does not pass through a singularity, then the corresponding mapped contour CF in f of s plane will encircle the origin as many times as the difference between number of zeros and poles of f of s that are encircled by S plane in contour C. Now, what do we mean by that? I hope all of you have understood what f of s is, what C is, and what C suffix f is. Now, there are another representations or notations which we need to study before actually understanding the mapping theorem. So we have n, the formula that is given as n is equal to z minus p. So here n is nothing but number of encirclements. We have seen the method to count the encirclements around origin. So n is number of encirclements of origin of f of s plane by C of f. Please try to visualize the diagram. In S plane, we have a contour. In f of s plane, we have another contour. First contour in S plane is known as C, and next contour in mapped contour in f of s plane is known as CF. So by CF, how many times the origin is encircled is nothing but this n. Z is number of zeros of f of s encircled by C. Now here we are talking about S plane only. We are not talking about mapped contour. In original S plane, how many zeros of f of s are encircled by C is given by Z, and similarly how many poles of f of s are encircled by C, that is known as P. So suppose when we have only contour C, value of Z is known to us, value of P is known to us, how many zeros and poles are encircled by original contour C in S plane, that we know. And now after sketching CF, that is in f of s plane, the mapped contour is sketched. After sketching that, how many times this CF is encircling the origin, that is value of n. If this condition gets satisfied, Z minus P is equal to n, then we say that the mapping theorem is satisfied. That mapping theorem is true. I hope all of you have understood the definition now. So what this mapping theorem says in short, that if suppose in S plane we have contour C and in f of s plane we have contour CF, then the number of times CF encircles origin is equal to difference between the number of zeros and poles encircled by contour C in S-plane, right? Now, going ahead, we need to understand what is its significance in case of Nyquist plot. So for that, we need to understand the Nyquist theorem. Okay, before that, we will see some examples that will give you a clear idea how n is calculated from Z and P, right? Now, look at the examples here. In the examples, you will find that there are two contours that are considered. One is in S-plane, left side is S-plane contours, and right side we have f of S-plane contours. And here we need to pay attention to the directions also. Directions are given with the help of arrows, right? So the first example, C is the contour in S-plane, CF is the contour in f of S-plane, okay? And the CF is used, CF is calculated by using the mapping, that point wise each point is mapped to another point in f of S-plane, and then the contour is formed. So I think that is clear with everyone. We need not discuss that again. So in this example, first example, there are poles and zeros that are marked. Here in this example, there is only one pole, right? Which is encircled by C, okay? And so value of P is equal to 1. One pole is encircled. How many zeros are encircled? 0. So that is why value of 0 is 0. Value of Z is 0. Now, as per the mapping theorem, we have Z minus P, that is equal to -1. So the value of N must be equal to -1. And that is why we know that in mapped contour, the origin is encircled by CF only once and in the direction exactly opposite to the direction of contour in S-plane. So this direction is clockwise, and that is why this in mapped contour we have anti-clockwise. And so N is equal to -1, which is calculated as Z minus P, right? So same goes for the next example. Now in this example, the direction is clockwise of the contour, and we are encircling 1, 0 here. There are no poles. So Z is 1 and P is equal to 0. Z minus P is going to be 1. So N is equal to 1. So origin is encircled once, right? And in the same direction as that of C, right? So that is why here in CF also we have clockwise encirclement. Third example, we have one pole and 1, 0. So Z is equal to 1 and P is equal to 1. Z minus P, that is equal to 0. So there are number of encirclements that equates to 0. So there are no encirclements around the origin. So here you can see that after mapping, the contour is not encircling the origin. Origin is outside the contour CF. And that is why we know that the encirclements are 0. That means this point is not lying inside this particular contour, right? So these are the examples which give you the brief idea about how the mapping theorem can be visualized graphically, right? Now, there are some cases where 2 poles or 2 zeros are encircled. We have just taken the examples where 1 pole is there, 1 zero is there, 1 pole and 1 zero. But there might be other cases where we have 3 poles or 2 zeros, then vice versa, like 2 zeros and 3 poles, whatever it might be. But in that case also, the same formula is applicable. N is equal to Z minus P. And with the help of the direction in S-plane, we can actually calculate how many times the origin is encircled in by CF rather, in f of S-plane. And so we can get the actual encirclements. Now, what is Nyquist stability criteria? So the next point, we have come to the last part of the Nyquist plot. Here we will study what is Nyquist stability criteria, which is derived from the mapping theorem. What mapping theorem said? N is equal to Z minus P. we are going to use this theorem and we will apply it to our understanding of closed loop stability, then open loop stability, and then we will, after sketching the Nyquist plot in the usual manner, we will be able to comment on the stability with the help of mapping theorem. Right? Now, let us revisit what we discussed about zeros and poles of 1 plus GSHS. We know that the open loop stability can be commented on or analyzed with the help of open loop transfer function. Similarly, closed loop stability is analyzed with the help of closed loop transfer function from the location of closed loop poles. In the previous session, we have also discussed that zeros of 1 plus GSHS are nothing but closed loop poles of the system, and poles of 1 plus GSHS are nothing but open loop poles of the system, right? So if we need to analyze open loop stability and closed loop stability both, instead of analyzing OLTF and CLTF both, we can analyze zeros and poles of 1 plus GSHS, and we'll be able to analyze both the types of stabilities, open loop as well as closed loop stabilities. Now, here, right now we are interested in the closed loop stability, and so we will be considering only zeros of 1 plus GSHS, which are nothing but closed loop poles. Now, if we need to locate the zeros of 1 plus GSHS, it is nothing but locating closed loop poles of the system, with the help of which we will be able to analyze whether the system is stable or unstable. And that is why, henceforth, we will consider that f of s. In our previous discussions, we have considered f of s plane. So that function is nothing but 1 plus GSHS, right? Now, what do we mean by that? If zeros of 1 plus GSHS lie in the left half of S plane, the system is closed loop stable. That means there is no pole, closed loop pole of the system, or there is no zero of 1 plus GSHS which lies in the right half of S plane. Even if there is a single zero of 1 plus GSHS that lies in the right half, we can directly say that the system is unstable. So instead of finding out that, instead of inferring that all the zeros of 1 plus GSHS lie in the left half of S plane, we will just find out, we will try to find out the presence of zero of 1 plus GSHS in the right half of S plane, right? Even if we find the presence of zero of 1 plus GSHS, then also we can directly comment that the system is unstable. Okay, so now in this case, instead of analyzing presence of zero in left half of S plane as given in the notes, I'm reading out the notes. In right half of S plane, yeah, so presence of zeros in right half of S plane is checked. If there is a single zero of 1 plus GSHS in RH of S plane, the system is unstable. Okay, now we will see what notations or what assumptions we are making. First assumption that we have already made is nothing but our f of s is going to be 1 plus GSHS. Now what do we need? We need the contour in S plane, and then we have to map it to the contour in f of s plane. Now that f of s plane will be 1 plus GSHS plane. After mapping it, then we will try to count the encirclements around the origin. If it satisfies n is equal to z minus p, then we say that the system is stable because the mapping criteria is satisfied. Now let me elaborate this. Just a minute. Okay, so this is S plane contour. Now what we are doing is we need to understand that we need S plane contour which will be mapped to f of S plane, right? So this S plane contour is called as Nyquist contour, and as we have discussed, we need to check the presence of zero of 1 plus GSHS in the right half of S plane. We will consider the whole right half of S plane as the Nyquist contour as shown in the diagram. So this right half of S plane is assumed to be a semicircular area with radius r which tends to infinity, and this is r e raised to j theta, where theta is the angle